Hello, everyone. I am a postdoc at Berkeley University, but I'm currently based at CERN, and as Jared already said, I'm working in the tracking community in order to integrate tracking software for the Atlas experiment. And this is basically what I'm about to discuss. The focus of this discussion is to start with a brief description of how tracking works and why we do need a CDS and the software. At least the focus would be obviously on the Atlas experiment, how we are doing it, and I may be a little bit biased about this, but keep in mind that a CDS is a software which is designed to be experiment independent. So other kind of experiments will be able to use it. At least this is the project. So hopefully we will go together through different topics and try to address a few important questions, like, for instance, why tracking, what is it for, how we do it, how we do reconstruct the tracks, and what are the challenges that we are facing right now, and what are the challenges that we will face in the future. By future, I mean run for it and beyond that. So 2028, I suppose. And yes, as I said, we will also focus on the ACTS software, and that is open source software toolkit for the track reconstruction. You can find here some documentation, to get familiar with it. So let me start with the very basics and state the obvious. Tracking itself is one of the most important elements in high energy physics. Willingly or not, you are using it in your analysis, maybe directly or indirectly, because tracking is basically everywhere. You use it, for instance, for the construction of the electrons, muons, and taus as well as jet reconstruction itself, and also its calibration. In Athena, we are using track information together with calorimeter information to accurately calibrate the energy of the jets. This is what in jargon is called as global sequential calibration. We use tracking for the vertexing, and vertexing then is used also for track reconstruction and jet reconstruction, because you have so-called p-flow jets. But all of this obviously has an impact as well on the missing energy. And as you can well imagine, tracking is also a key factor, key elements in flavor tagging. So tracking information, like, for instance, the impact parameters, secondary vertexing, are the key ingredient for C tagging or B tagging as well. Also, tracking is used for computing the position of displaced vertices. So you will have displaced tracks. So that is, for instance, highly used in long-lived particle searches and so on. Pilot projection, extremely important for basically everything, including the energy calibration and so on. And finally, but not the last element, is the alignment of a detector itself. So all of these areas use tracking information, but you also have to think that you do have an offline environment, like for an analysis or reconstruction, but you also have an online environment, commonly referred to as the trigger, and tracking is used there as well. In fact, the same software, the same algorithms used for track reconstruction at offline level is also used at online level. And we will go back to this point a little bit later. So again, stating the obvious, track reconstructions aims at reconstructing the trajectory of a particle. So you do have charged particles, you do have a magnetic field, that means you do have a helix, and you basically have 5 different parameters to describe it. So you do have 2 different angles, you do have impact parameters, and you do have the charge of momentum of a particle. And the aim here is to compute these quantities with the higher accuracy as possible. And there are obviously demanding requirements from tracking. For instance, you do want extremely good momentum resolutions. You do want to go as low as possible with the momentum of the track reconstructed. You do want to resolve nearby tracks, and as well here we will go back on all of these points later. And you do also want an excellent impact parameter resolution, because all the areas that I've mentioned before relies on this kind of measurements. So how is it working, at least how we do it in Atlas? So the Atlas track reconstruction sequence is defined here. So you do have a series of steps, series of algorithms. So you start with data preparation. So imagine you have particles going through your tracking detector. You do have sensors. You do have energy deposits in this sensor, which usually are pixel detectors, for instance. You do have clusters of energies. You identify the clusters, and from the clusters, you define 3D measurements of these hits, which I usually call space points. These 3D measurements are then used in the next stage. The next stage is the pattern recognition, which means that amidst all of this 3D space points, you want to identify triplets of space points which are compatible with the helix trajectory. And this is quite a huge problem. It's a combinatorial problem, and you can think of how difficult it is when you have, for instance, 10 to the 7 space points just in one single event. So this is where the major of the CPU consumption comes. Once you have identified these triplets, which we usually call seeds, then you propagate the trajectory to the other layers of the detector. This is the track finding step. So you start from the seed, you go to the next layer, you find a new compatible space points, then you move to the next layer, and so on till you reach the end of the detector. And after this step, then you have to sort this out and try to identify, for instance, hits that have been wrongly attributed to the wrong track, and so on. This is the so-called ambiguity resolution step in Atlas. And at the end of this step, you do have some tracks, and you can use the tracks to then identify the vertex position. So this is basically the workflow of the track reconstruction sequence in TNAT list. Obviously, different experiments may have variations of this approach, but I'm not going too much into the details of how they do it. But obviously, you do have several topologies of events that can occur. Here you can see a snapshot of all of them, but I will go through these points and see briefly how Atlas enters it. So let's start, for instance, from the primary vertex position. So this is basically the place where the interesting interaction has occurred. By interesting interaction, we identify it by asking ourselves which is the primary vertex, which is the hard scattered vertex. And we want to distinguish it from other interaction that may have occurred, because you do have multiple interaction happening at the same time, because you have 2 different beams of proteins. So you do have a primary vertex, and you really want to distinguish it from non-interesting collisions. This is the pileup. And in Athena or in Atlas, the default identification method simply relies on the sum of the squared of the PTs. This is how we defined the hard scatter vertex. And as of now, I mean, we are in run 3, so we have something like around 60 collision happening in parallel. But as of now, the average of the hard scattered events is only 1 on average. But if you go and take a look at what's going on in the future, then the pileup will go from 60 to something like 140 and 200. So in the future, you do have to change this paradigm, and you will find out that we are expecting something like 2 different hard scattered vertices happening on average. So we will have to cope with this. But another important thing is that the criteria we choose for identifying the hard scattered vertex is actually not the best one for all the space spaces. You can take a look, for instance, at the plots on the right. This is the VBF H2 invisible, and there you will see that by using the default vertex identification methods, you have a drop of efficiency of something like 10%. In that case, the analysis is actually exploring a different way of identifying the scattered vertex. In that case, the selection method will simply be on the sum of the PTs. And in that case, you see that the blue dots have basically reach almost a 100% efficiency. So this is quite a peculiar case. You can see more details in the publication itself. It's quite interesting indeed. So this is the primary vertex. Then you do want to go, as I said, as low as possible with the PT when you reconstruct the tracks. The problem there is that the lower you go with PT, the more the particles tends to bend, obviously, which means that when you do track reconstruction, then the search windows for the next compatible space point when you do the track finding is quite large. And if it is too large, then you do obviously more space points and more combinatorics, and it's very easy basically to have things exploding. And you can see that the computational complexity is a little bit too much. So the problem here that is indeed this, and this poses a limit on how low you can go with PT, and obviously this limits also the analysis, because at that point you do have a space that you can't reach. So the aim is going as low as possible in order to give more data for the analysis. Then you have cases in which you have particles that can travel through your detectors before decaying. So you do have displaced vertices or displaced tracks. This is what in Atlas is usually called as LRT, or large radius tracking. So this is an additional step that we do have in the track reconstruction, which has some loose constraints on the impact parameters, for instance. And you can see on the bottom what is the effect of the large radius tracking compared to the standard tracking, which has quite strict requirements and constraints on the impact parameters. So you can see indeed that long-lived particle searches actually gain a lot by using this different approach. And finally, the last topology I'm going to discuss about is perform track reconstruction inside a jet. So this is what's usually called as tracking in dense environment, or TIDE. And what happens here is that, well, you have a jet, so you have a group of collimated particles going all in one direction. If you can take a look at the plot on the bottom left, you can see that the majority of the tracks of the particles is extremely close to the center of the jet. So they are extremely close to each other at the point that the separation between two different tracks is compatible with the pitch of your sensor. That means that when you take a look at the clusters of the energy deposits in a sensor, then you do have overlapping clusters of energy coming from two different tracks. This is a problem. This is what we call merge place pixels, and that has a huge effect on the tracking efficiency. And this is why we have a dedicated reconstruction chain for this kind of environments that use neural networks in order to identify these merged pixels, these merged clusters of energies. And you can see that by using this TIDE workflow, you actually gain some efficiency with respect to the baseline. This is the bottom right. So yes, these are all, let's say, the different topologies that you may encounter, and the track reconstruction itself has to cover all of this. But the problem is what's going to happen in the future. I mean, already right now, we have quite a challenging environment. We started from round one, and from there we kept increasing constantly the energy, the center of mass energy. So we started from 7, 8, whatever it was. Now it is something like 14. And we also increase the luminosity. So higher the luminosity, the more pileup you have. So you have a lot of concurrent interactions, which means that the events are more populated. You have a lot of tracks, a lot of space points, and this is a problem. And in the future, it's even going to be worse. So as of now, we have something like 50 of pileup. As I said, in high Lumi or run for in general, we are expecting something like 200. This means that we do have to upgrade both on the hardware side and the software side. So on the hardware side, you may have already heard about ITK. This is basically the new tracker that we are going to use for high Lumi. And the reasoning is simply that what we currently have as of now is not sufficient. Our current inner detector was designed something like 10 years ago. As I said, the running conditions back then were much easier than they are right now. Obviously, back then it was already considered challenging, but by today's standard, it is not at all. And already in 2016, the design parameters already exceeded the design. So this is not sufficient for high Lumi, not at all. So we have to introduce this new detector, and there are some features that I'm not going to discuss here because that's not the topic of this discussion. But you can, the key points that we extended the pseudo rapidity range, the coverage from the 2.5 to 4, and we will improve the granularity of a detector so that you will be able to distinguish between two different, two close by particles, even if you're running on 200 pileup, which is not what the inner detector right now would be able to do. And we also have the HGTD. This is this orangish thing in the forward region, which will also provide some timing information. So that will open the door to forward tracking. So this is quite interesting. But as I said, also the software has to be changed, because as of now, we can hope to survive, not easily, at least. And you can well imagine that given the computational challenge of a tracking component, that is what is draining the CPU consumption. The combinatorial problem of track finding and so on, this is quite expensive. And if we still use our current software also for run for, then we will not be able to cope with it, because we do have some CPU constraints, CPU budget constraint for the future. And as I said, the offline tracking software is also used online, meaning trigger, and at trigger level, the constraints are even stronger, because you must be extremely fast, you must consume even less memory, and so on. And if you don't manage to do so, then you lose events and you can't recover from them. What's lost is lost in that case. So this is why we need a modern and maintainable solution. Also because the current tracking software we have in Atlas is old, is 20 years old, at least, which means that in all of these years, it has gone through a lot of upgrade campaigns, which basically means people start modifying it in order to do the job that the software was supposed to do, but that simply doesn't mean that there was a big design behind it. The original writers of the software are most likely not even in Atlas anymore. So what actually ends up is that we do have a software which for the most part is even unmaintained, and no one really is an expert on all of it at all. Sometimes you do have just students, physics students, that are given a task to write some piece of code, but they haven't not even an experience in writing software. But the point is, you want to write something that works, because we are physicists and we are writing software for making physics. But you can imagine in what bad situation the current Atlas software is. But thankfully, CTS will solve this problem, because we are specifically designing it in order to be maintainable and easy to modify and write. And as of now, my main focus is on the CPU, but of course there are R&D lines that are exploring also other solutions like heterogeneous environments. So we will go back on that a little bit later. So yes, this is basically what the situation is. The software was designed to deal with what the run one condition were. It has been modified so far in order to cope with the run-free conditions, but for the run-for, we have to write a software that will be able to manage this, these so crowded events that we foresee for the future. And this is not easy at all. So what is a common tracking software or a CDS? So this is a generic framework, experiment-independent open source toolkit, which has been developed mainly from Atlas folks. So it is extremely inspired by how the Atlas reconstruction chain is done. It is written in C++ 17, but we are thinking also C++ 20, but the baseline is 17. I don't think, maybe root has been readapted to C++ 20, but I don't think Athena is planning to use it quite soon. Oh, sorry. So the point is that this software will provide some algorithm for the track reconstruction. And the point is that this is not limited to Atlas. It is something that any kind of experiment may use. So the design of the software is supposed to be completely detector agnostic. It doesn't have to know anything about the technology using the detector, how it is designed, or anything like this. Obviously, any algorithm will be able to produce a tuning of the parameters of their own, so that the software will be able to work efficiently in any of these experiments. But yes, this is basically the key point. And you can see here a little bit of a sketch of all the different components that make a CTS. And the design here is that a CTS is supposed to be thread safe natively. So it supports a parallel code execution. We had a lot of attention and writing optimized data structures, a lot of attention of memory management, and all of kind of stuff. And as I said, this is something that's supposed to be used also by other experiments. And as of now, other experiments are already trying to introduce it and use it in their own software, in their own environment. And you can see that there are already a few publications available, which explicitly quote a CTS as a software used. So this is very good. So what are the main concepts of the CTS software? So as I said, there is built-in support for the parallelization. So you do want to support this parallel execution within different events. even without an explicit technology binding such as TBB. So thread safety, which is assured by concurrentness, basically applied everywhere. Contextuality, so you do have a way of handling objects which are supposed to be shared between different algorithms or events. And especially it's quite important, for instance, for the geometry description and so on, of magnetic field and the calibrations, for instance. The key concept as well here is that you want to decouple the configuration of an algorithm from the actual initialization, the execution. So the user will be able to define a configuration which will contains parameters that are not supposed to be changed during the execution. You do have options which will contain mutable objects, like for instance the beam spot position of magnetic or alignment of things like this. And then you do have the algorithm itself that will use this this object that the user will configure as they see fit. And the algorithm will simply adapt according to what you give them. Then the flexibility, as I said, a CTS will be used by different experiments, and you can't force every experiment to use the same event data modeling, for instance. So you do want to have an internal representation of things. It's in this case is the green elements in this picture. So generic mathematical or algorithm models. Then you do have experiment-based specification, like red things, like for instance, the Atlas magnetic field. The measurements by these are all experiment specific, and ICTS must know nothing about it. And then you do have a bridge between these two words, which is the blue things, the blue elements in this picture. So the intermediate objects, which will let ICTS talk with the experiment itself. With these elements in place, you will be able to perform reconstruction, track reconstruction in any experiment. This is how we are trying to design this. And this concept also applies to the event data modeling. So in these specific slides, you see, for instance, the main concept of how a track is defined. The idea here as well is to decouple the interface and the storage implementation, which is experiment specific. So you do have, for instance, an internal representation of the track, which is in a CTS. And then you have whatever object your experiment is using for defining a track. And in the middle, there is this connection that will let a CTS talk with whatever experiment implementation you do have. For more details, you can find a very interesting presentation from Paul at CHEP 2023, which was something like 2 weeks ago, something like that. So yes, so the main concept is interface on one side, internal representation of the CTS, and the other side, which is the experiment side, so the memory backend, and in the middle, a user-facing API that will let things talk. So yes, I mean, if you want to integrate then all this concept, this software in an experiment, then you have to take different actions. So you do want to do some liaison between the EDA and the event data model definition. So as I said, there is an internal representation of a track, for instance, and how Atlas defined a track. And in the middle, there is this liaison. And once that is established, then you have to modify and propagate this to all the different areas of the track reconstruction. So reconstruction, like the seeding, the Kalman filtering, the vertexing, as well as all the different clients of tracking. So nuance, alignment, flavor tagging, and so on. And there is already, as of now, in run 3, a successful example of this process of integration. This is the vertex reconstruction already in Atlas. And you can see here what is a performance with respect to the old and default Atlas vertex reconstruction. So the point is that before run 3, there has been already this effort of integrating a CTS into Athena. And the first thing is that we wanted to write from scratch the vertex algorithm, the EMVF, from Athena imported into a CTS. So the algorithm itself is the same. It has just been written inside a CTS. And you can see that on the bottom right, for instance, just by doing so, you do have a 40% increase in the in the CPU timing. And this is why, as of now, the SCTS vertex reconstruction is the default vertex algorithm used in Athena in run 3. You have a 40% improvement in the computing time, but at the same time, you have unchanged physics performance. So this is a win situation for everybody. From a CTS side, which has demonstrated that it is quite a competitive and valuable software, and the Athena, which has gained in CPU performance and memory as well. And the plan here, starting from this experience, is to also migrate all the other components of the track reconstruction. So we are currently working and introducing the clustering, space point formation, shading, combinatorial camera filter, and so on. Unfortunately, it is still under development, so I can't show you anything. But we are proceeding, and we have quite encouraging results as of now. However, there is a problem, as I said. So what happens if you go to trigger? Trigger is quite a difficult area because of the constraints, technical constraints. And it is if you limit yourself to the offline environments, you may well live with a CPU-based track reconstruction workflow. It is most likely. If you will go on the trigger side, then you'll have to think about other solutions and, for instance, an heterogeneous computing, an heterogeneous environment. So you will have to explore the possibility of a GPU, CPU, FPGA solutions altogether. Which is what we are currently doing. So, for instance, the EF tracking effort is going exactly in this direction. But as of now, as of run 3, we are still running on CPU only. I think in Atlas there are GPU pieces of code, but we are not using it for production itself. And the point is here that in order to survive to the constraint and still provide high quality track reconstructions, on the trigger side, there are a few differences with respect to the offline counterparts, even though technically the offline algorithm are the ones used also to the level. There are a few differences now and then, especially when it comes to pattern recognition. And also the strategy by which tracking reconstruction is performed is different, because at online level, tracking is a multi-stage approach. So you run tracking multiple times in regions of interest. So on the bottom right plot, for instance, you see what happens for instance, for BJet triggers. So you run tracking 2 times in that case. Well, 2 times up to run 2. In run 3, we have added an additional step, which is kind of a pre-selection in order not to perform full-scale tracking with pflow, which would be way too much. So as of now, we are actually running 3 times for BJets. But yes, I mean, the reason here is a little bit different, and how you perform track reconstruction is different. Obviously, I will not go into the details because that's a little bit way too much, and every single signature has its own way of doing things. So muons, electrons, taus, and beads have different strategies. So that would be out of scope, I would say. But yes, as you can imagine, SCTS has as well a GPU R&D line. And it is still under development. So as well here, I don't have public results yet. There are some presentations that have been done at Connecting the Dots 2022 by Bonke, for instance. You can take a look at them. They are quite informative. But the point here is that we have some pilot studies on GPU, which then naturally led to this R&D line. So the problem, however, here is that if you want to offload the entire tracking chain to the GPU, then you have problems because, for instance, not all of C++17 features are available on GPU. So you have to find other solutions there. You have to know exactly the memory you want to allocate before running. So for instance, what happens if you have space points, so you are reconstructing seeds, how do you know how many seeds you are going to produce? How do you allocate enough memory? The solution is you run it twice, and that's the solution so far. But I mean, there are a lot of requirements as well that you have to meet. For instance, you perform track reconstruction on GPU, well, that means the physics performance must be the same, if not better, than the CPU counterpart. Then ideally, you will also want to share the EDM definition between GPU and CPU, but that is still under discussion as of now. So we do not have it yet, but we are working on that. So yes, I mean, the application obviously would include having GPU-based algorithms for our different areas. For instance, the pattern recognition algorithms, which would help us improve quite a lot, just because pattern recognition is quite expensive already. So that would be quite a nice area to have it. But you can also see here an example of a Kalman filter in this case on GPUs, and you can see that the results are really encouraging already. So this is a large speed up, for instance, in the Kalman filtering up to 100 tags. So this is quite promising. And when it comes to the code itself, or how this the GPU area is developed or structured, then you see here a representation of all the building blocks. So track CC is the full-scale demonstrators that will basically provide the reconstruction chain. It is obviously based on Atlas-like reconstruction, exactly as SCTS, because the same reasoning, the majority of developers is from Atlas, so we are bringing the knowledge from there to SCTS. And this uses different elements. So you see dtray, algebra plugin, Coffee, and Beckman. So what are these things? So algebra plugin are simply an implementation of the linear algebra functionality. So we only implement what we need. So we go up to a metric of size 8 from the backend side. So the storage, you do have, you are internally using Eigen or standard library like STArray and so on. And from front end, you define the mathematical interface of it. You're using basically the same interface that you may find for the standard library, for instance. Beckman is the memory management. This is what will provide heterogeneous memory management in CTS GPU. And it provides standard-like interface and device allocate memory and so on. Other elements are Coffee and dtray. I'm going very quick about these things. So Coffee is a vector field library, so that is what we use for defining the magnetic field in Atlas on a GPU. while D-tray is the library for the geometry and the propagation in this field. And you can see here the representation of the Atlas magnetic field on a GPU. And you can see here also the lookup time for the different technology. You can see that the GPU is quite faster than the CPU counterparts and so on. And when it comes to the propagation, which is one of the most expensive processes you have in track reconstruction, because you have to propagate from one layer to another in a non-constant magnetic field. Then you can see that there is a huge speed up with respect to the CPU counterpart. And this is quite interesting as well. So there is a lot of things that you can gain by going on a GPU and perform track reconstruction there. But I mean, this is an overview of the CPU and the GPU R&D lines. Let me open just a window because that's a completely word of its own. That is the machine learning tracking with machine learning, and yes, SCTS as an R&D line in this context, which is called ESA-track. And you can well imagine that machine learning is technically already used in track reconstruction for different tasks, and not only in tracking, but basically everywhere. But we are evaluating other concepts or other strategies for track reconstruction, heavily relying on machine learning. So the ESA-track project then evolved in GNN for ITK, for instance. That is basically using a GNN for performing the track reconstruction. So every single hit is a node, and the connection between two different hits is the edge. And the point is, what are the right edges and what are the right nodes that make a track? So that is the main concept. But you can also think about using machine learning for vertical reconstruction. And there are a lot of different studies that Atlas is doing as of now. But as I said, I don't know what, I just want to open the window here and give a very quick look at this. I will not go into any of this because that would take something like more than 1 hour of another talk and so on. So yes, so this was everything that I wanted to discuss. So we have discussed about the track reconstruction on high energy physics, how complicated that is, what a challenge that is, and what are the reasoning that have driven us to write and develop a tracking software that is generic and supposed to be used by different experiments, which by its own, it's, as far as I know, something that has never been done before. So this is quite an interesting development when it comes to high energy physics, because I'm not aware of any commonly used software throughout different experiments. So this is quite interesting. And the point is that a CTS will provide high physics performance at a lower CPU expense. So you will have upgrades from the CPU consumption time, from the memory consumption time, just by using this software, which will provide better, equal physics performance than the current software that we have in Atlas. And as I said, there are different R&D lines here that have been actively developed. So CPU side, GPU side, and machine learning based line. So there is a lot of work going on. And for run 4, we plan to completely replace the Atlas track reconstruction algorithm software with a CTS. And yes, so do you have questions about this? So this was what I wanted to talk about.
Thanks, Carlo. That's super great, and exactly I think what we're hoping to see. So that was super nice. So Yeah, I could ask a question too, but I prefer to leave it open to other people first. And Hector is not shy, so why don't we go to him?
So, it was really nice. Oh, thank you very much. I wanted to ask, I think it's slide 23, when you talk about the CPU studies. I think.
What's
Sorry, the
best?
GPU studies. I think it's, yeah.
GPU. This one.
Yeah, this one's fine. Maybe the one in which you saw the improvement by applying CPU, yeah, GPU, sorry. Yeah, I think this one's the one. So, okay, it doesn't matter. So the actual question that I had is, do you know if, look, like, is ACTS particularly good in the sense of, is it easier to implement in a GPU context than the old standard of trigger that we use in Atlas, of tracking that we use in Atlas? Or is this an improvement that you would get anyway without ACTS? I'm wondering, because ACTS in principle, it's easy, more easily parallelly, say, however you say, to make it more parallel. But so I'm wondering if this is specifically good for GPU implementation, or is this something that you would get anyway?
Yeah, you were breaking a little bit. Can you repeat the question? Sorry.
Yeah. So I'm trying to understand how much of the improvement given by the GPU is because ACTS is good, like the ACTS way of doing things is better at implementing a GPU-based solution, or is just because you would get a similar improvement when implementing the old standard of tracking in Atlas, for example?
That is a good question. I don't have numbers. I don't think that they have analyzed this yet in full depth, because we're still developing it. But what we know is that ACTS, well, CPU and GPU R&D line are technically separate as of now, so we want to merge them at a certain point. So technically, it's two different groups working at that. So the majority of the gains come from the careful management of memory consumption and the way we define the basic object and so on. So that is already something that can improve quite a lot of performance. Of course, we are developing things in order to be as parallelizable as possible. And our studies that we are still performing have already showed that writing the same algorithm in GPU and GPU show that the same algorithm GPU is much faster than the CPU counterpart. I'm not exactly sure exactly where that speed come from. So that is something that has to be studied quite deeply just to understand it better.
Okay, thank you.
Other people questions? What else? I'll ask. Oh yeah, perfect. Rick, go ahead.
So very, very nice talk. I'm really impressed with the ability of ACTS to separate out the generic tracking algorithms, and the parallelization of them from the experiment specific characteristics and the specific computing platforms. So that's really, really nice to see. And I know very well how difficult that to achieve that is. My question is sort of related to the challenges of separating out the generic tracking algorithms from the specificity of the experimental characteristics, and in particular if we go to slide 11 or 12, maybe 11. Yes, yeah. So here you talk about long-lived particles, and the challenges and sort of the ideas of how to get tracks from them. One of the experiment-specific characteristics of a tracker is its material budget. So, how much material is there? And different experiments will have different amounts of material in their tracker. In particular, I want to say that the CMS tracker is pretty heavy. There's a lot of material. This one. That creates a lot of interesting challenges. And I can imagine, other trackers will have less material or more material. But with more material comes, an additional type of interaction, which is called a nuclear interaction, where you have a nuclear particle impacting within the material of the tracker, and then just producing a incredible high multiplicity shower. It's almost as if the tracker itself were a calorimeter, and that can lead to a huge amount of additional tracks and hits from those secondary tracks, and that leads to a lot, very high. It can lead to a much higher fake rate in terms of track reconstruction. I was wondering, how does ACTS deal with those type of situations?
All right. Well, in this slides, I didn't mention geometry of material budget as well. But in a CTS, there is also a geometry that is developed. So basically, you take wait, it's on, I don't recall which slide it was. Okay, so we do have a way of defining all the different elements of a detector. So you can see here the different representation from different experiments. And we do also have a way, let's say, a description of the material budget from an experiment. So from that point of view, the description of the detector is taken into consideration. Then the point about having nuclear interaction and the showers, I'm not exactly sure about the implementation, but you do have, during the propagation of the tracks, a way of plugging this kind of experiment dependent or reaction and so on. That depends on how on the propagator and the actor during the CKF process and so on. It is technically possible, not though really sure we are already in the stage that we are actually doing it for an experiment. But technically the possibility is there, because we do define objects, abstract classes or interfaces that the experiments will be able to pick and add their own implementation of different things. So this is how on a CTS we handle experiment-specific things like the things you're mentioning. So
I see. So that's really nice. So that it's extensible in that sense, and
yes, it is.
Yeah, that's okay. That's really nice. This is, I have to say, I'm really very impressed with this whole thing. Very nice.
Yeah, Rick, you could convince CMS to take it on, which they haven't.
Yeah.
Sorry, Carlo.
Go ahead.
So I was going to ask a practical question, and then I have some other questions about the talk. So practically, you had some really nice links in this talk. Are you, aside from the recording, what you're doing, are you able to send me, post some of the slides that I can share with everyone for later?
Yes, just let me know if I can upload them somewhere, or I can simply email you.
We're in the process of putting a website together and such. For now, if you're willing to email them, it's probably the easiest thing I can share with everyone. Yeah. Thanks. Yeah, that'll be super helpful. So I had, I guess, two broader view questions. So one thing that always concerns me about ACTS, and I know I'm not the only one, is how much of a penalty we pay in making things, experiment agnostic. And I know that you work heavily on this to try and make the performance of, the track reconstruction, reach the level, that we have in the experiment specific, Athena. And so, given that this is always, something that's being worked on, can you comment? You had the super big improvement on the vertex reconstruction. I've seen those nice plots before. So what was it in moving to, yeah, thank you. I forgot to write the slide number down. What was it that made things so much better in ACTS? Like, can you point to something specific or a few specific things that gave you that big improvement? Even for the same seeder, there's a big difference.
Yeah, I mean, but the point here is that the ACTS vertexing is the same algorithm that Athena was using. So basically, the upgrade, this 40% improvement comes from simply better memory management, better definition of object, and so on. Because how Athena software is written. We have a lot of allocations or pointless loops and things like this. So there is, when people develop in Athena, they don't really care too much about, oh, this algorithm goes like n squared, maybe we can make it n log n or things like that. ACTS is trying to do that. That is as well another point. But you're right. I mean, it is quite complicated to write an algorithm or the software itself, which is supposed to work on something you don't know. I mean, take a look at what we are doing for the idiom. I mean, we have found a way to have an internal representation which is able to connect to whatever the experiment is providing. I give you the example of a tracking. I am currently working on the space point, but I mean, it is extremely complicated, and most likely in some places we are even paying a price for this flexibility. But I mean, we are extremely careful when we develop that memory consumption is reasonable or even better than before, and some studies already show this, as well as extremely careful and thoughtful when it comes to the timing, because you may have same performance, but if your algorithm is low, no one will use it. So this is a key point of ACTS development.
Sure. No, that makes sense. And then I guess maybe a related question. I suspect I can guess your answer, but I'll ask it anyway, because maybe there's things I haven't thought of. At the beginning of the talk, you were mentioning how, the challenges that Atlas faces in having software that has been written by people that have left, 15 years ago, and that is not so reproducible and uses old technologies and the such. So, ACTS is being written with C++ 17 in mind, and at some point, maybe C++ 20, and then I would have a separate talk to ask, why that's needed, but that's a separate question. But what is being done to try and make sure that this software framework that's being written 15 years from now will still be readable and maintainable and kept up to date, so that we don't make that same mistake?
Yes, I mean, that is one of the big questions, I would say. But we are trying to make self-contained functions, self-contained classes, but do one job only, and which is one of quite important things to do, I would say, because that would make things much easier. When we are very careful about documenting things, which is something in Atlas never happens, because you have lines of code, you have no idea where magic numbers come from. And you will find that there is a lot of documentation, both in the code itself and in a dedicated website, because we're using Doxygen to produce that documentation. So you have all the classes, all the methods and everything It is not most of the time easy to navigate through the code. That is something that we have to solve because everything is templated. So even trying to understand what the propagator T is, what kind of class it is, what are the methods is complicated. So on that side, we have to improve. But I mean, yes, we're trying to document things, and so that if a developer goes away for one reason or another, someone else will be able to step in and already know what's going on. So this is what we're trying to do.
Makes sense. Yeah, it's not an easy task. So yeah, I understand. Okay, that was my guess. Okay, thanks. So that was super thoughtful. Are there any sort of last questions for Carlo? It seems not. So thank you again, Carlo. This was absolutely wonderful. And when you share the slides, I will point people to them so we have it. And I think this is
sure. Thank you so much for having me. And
yeah,
yes, I will
thank you
forward
again.
Slides.
Yeah, and I'll let you go and enjoy your dinner, I guess then. So
I've already had dinner so in advance.
Okay. All right, go have some dessert or a drink before bed. Yes.
Yeah. Okay. Thank you so much. Have a
All
nice
right,
day.
thanks again, and thanks a lot, everyone. Bye-bye.
Bye.
Thanks. Bye.
Thank you. Bye.